Hello everyone, so let's keep looking at Poisson processes. QP126, we're going to derive the gamma distribution. Basically, we have some magical unicorns that are wandering into your backyard at random. Evidence suggests that arrivals occur independently and at a constant average rate of 4 per hour. Okay, it's a Poisson process, right? So now we let t sub k be the waiting time in hours from t equals 0 until the kth unicorn arrives. Very similar setup to QP111, but in QP111 we are deriving the exponential distribution, which is just basically a special case of the gamma distribution when we're looking at the first arrival, but in this case we're looking at a general kth arrival. So exponential is a special case of the gamma. Gamma is going to have a much more complicated PDF than the exponential did, and that's why it's going to be a hard problem, right? But the setup is exactly the same. So for k equals 3, first of all, what is the probability that the third unicorn arrives within the first 15 minutes of observation? So compute the probability that t sub 3 is less than or equal to 0.25. So let's do part A. So first of all, if I have my hour right here, well, obviously 15 minutes is going to be 1/4 of that hour. So that's why we're trying to find the probability that t sub 3 is less than or equal to 0.25, or 1/4. We have a Poisson process within this hour, derive the Poisson distribution in QP number 1. So we have a rate of basically 4 unicorns coming per hour. So just like in QP 111, let's find a way to relate this to the Poisson distribution. So we're trying to find the probability that the third unicorn comes within the first 15 minutes. So what that means is I have my first unicorn come within the first 15 minutes, then I have my second unicorn come, and then I have my third unicorn come. So what's the probability of this? And then obviously after my third unicorn comes, I can have any number of unicorns that also come within this first 15 minutes. So just like in QP111, right, if we let x be the number of arrivals within the first 15 minutes, then we can relate this to the Poisson, right, because x is going to be Poisson distributed. All you have to do is realize that the probability that the third unicorn comes within the first 15 minutes is basically the same as the probability that at least 3 unicorns come within the first 15 minutes. So the probability that x is greater than or equal to 3. So for instance, if I have 10 unicorns come within the first 15 minutes, then yes, the third one still came. If I have 1,000,000 unicorns come within the first 15 minutes, then yes, the third one still came within the first 15 minutes, obviously. So because the number of unicorns that come within the first 15 minutes could go up to infinity, right? This is going to be much simpler to express as 1 minus the probability that basically x is less than or equal to 2, or x is less than 3, right? That's because the probability that the number of unicorns that come within the first 15 minutes is less than 3 is just going to be equal to the probability that 0 unicorns come within the first 15 plus the probability that only 1 unicorn comes plus the probability that 2 unicorns come. And obviously x is Poisson. We know the PDF of the Poisson from QP1 where we derived it. The probability that x is equal to little x is just going to be e to the power of negative lambda times lambda to the power of x divided by x factorial, where lambda here is the number of expected arrivals within the first 15 minutes, and we're given that the number of expected in an hour is 4, and events are occurring independently at a constant average rate. So if we expect 4 to come within an hour, well then we're just going to expect 1 to come within a quarter of an hour, right? So therefore in our case our lambda is just going to be 1, so I'll just replace that like so. Now obviously when lambda is 1, if we raise that to any power, it's still going to be 1, so we can basically just erase this from our density function. So now let's just plug in these x values into our PDF. So the probability that x is equal to 0, when we plug in 0 here, we're just going to get e to the power of negative 1 divided by 1, right? Now when we plug in x equals 1 into this PDF, we're again going to get e to the power of negative 1. When we plug in x equals 2, we're going to get e to the power of negative 1 divided by 2. So these right here collectively sum to basically being 2.5 times e to the power of negative 1. So 5 on 2 times e to the power of negative 1. So that's the probability that x is less than 3, that the number of events that occur within the first 15 minutes are less than 3. So 1 minus that is going to be the probability that the third event occurs within the first 15 minutes. So I take 1 minus basically 5 on 2 times e to the power of negative 1. And when you actually work this out, we're basically going to get something along the lines of basically it's going to be 0.0803, something like that. So roughly 8%. So this right here is the final answer for part A. You can see it wasn't too tricky. And 8% is pretty low, which is what we would expect because we're only expecting to get 4 in the whole hour. So the probability that at least 3 come within the first 15 minutes, yeah, we expect that to be pretty low. Okay, so now let's go on to part B where we're just kind of generalizing this. We're finding the probability that t sub k, so the kth event, comes within the first t time, right? Okay, so now let's just be more general. Let's just say we have some big time interval. Let's say that events occur with some rate lambda in this time interval. So we have some smaller time interval in here that is t. Let's say it's like this. And we want the probability that the kth event occurs within here. So all that means is that we have at least the kth event occurring. So we could, maybe this is the kth event, and then we could have any number after. So just like we did up here, we can do the exact same thing. All you have to do to relate this to the Poisson is just by realizing that this is basically the same thing as saying what is the probability that at least k events happen within this time interval. So I'll just come down here to make some more space. So if we let x be the number of of arrivals within this time interval t, well, x is going to be Poisson distributed, so we can calculate this. All you have to do to simplify this, because x can go up to infinity, it's going to be easier to express the probability that x is greater than or equal to k as 1 minus the probability that basically x is less than k, or x is less than or equal to k minus 1, whichever one you prefer. Now, the probability that x is less than k is just going to be the probability that x equals 0 plus the probability that x equals 1 plus the probability that x equals 2, all the way up to plus the probability that x is equal to k minus 1. We can obviously write this more simply in summation notation. It's just going to be the sum from basically, let's have our iterator be j equals 0 to k minus 1 of the probability that x is equal to j. And if we have lambda arrivals within this bigger subinterval, well, then we're just going to have lambda times t expected arrivals within this subinterval t. That's just assuming that t is expressed as some fraction or some multiple of basically the time units that lambda is using. So if lambda is arrivals per hour, well, then t might be like it was back in part A, like 0.25, so for 15 minutes. Or we could have t be equal to 2, and if lambda was accounting arrivals per hour, then this would count the number of arrivals within the first 2 hours, right? So if this is our rate parameter right here, well, x is Poisson distributed. So again, the probability that x is equal to little x is just going to be e to the power of negative lambda t times lambda t to the power of x divided by x factorial. So let's just plug that into our summation notation right here. Actually, I'm going to change my iterator to be x. When I do that, I can replace this with a PDF, which is e to the power of negative lambda t times lambda t to the power of x divided by x factorial. So this whole term right here is just going to be 1 minus that, right? So this right here is the probability that x is greater than or equal to k. And we know that the probability that at least k events occur within that time interval is just the same as the probability that the kth event occurs within that time interval. This right here is the answer for part B. You can see it's very similar to what we did in QP 111 with the exponential distribution, but now we have this sum, so differentiating this in part C is going to be a lot harder. Okay, so now for part C, we just want to find the PDF of the gamma distribution. We already know basically the CDF, which we calculated from part B, so now we just need to differentiate it to get the PDF. Basically what we're given up here is we have some t value, and we know basically the area under this curve, the probability that t sub k is less than or equal to this value. So given the area under the curve, all we want to do is just find the PDF, which is just basically the function that represents this line right here. So again, fundamental theorem of calculus, if I know the area under the curve and I want to find the function, I just have to take the derivative of this. So that's what we're going to do. Okay, so to take the derivative with respect to t of this, well, we know that the derivative of 1 is just going to be 0, so we can just basically ignore that term, right? So we just need to take the derivative of this now. And now this is a somewhat tricky derivative to calculate. Basically, we can pull the negative out to start, and then let's also just pull out this term right here because it does not depend on the iterator of this sum. So we have e to the negative lambda t times the sum from x equals 0 to k minus 1 of lambda t to the power x divided by x factorial. Okay, we're multiplying this term times this term, so a little product reaction. The derivative of this one is just going to be negative lambda times e to the power of negative lambda t. And then for this next term, we can just rewrite this basically as lambda to the x times t to the x. The derivative of this one is just going to be the sum from x equals 0 to k minus 1 of lambda to the power of x times x. When we take the derivative here, right, we're going to get x times t to the power of x minus 1. And that's all divided by x factorial. These terms are constant relative to what we're taking the derivative of, so that's why we can do that. Okay, so those were our derivatives, but we still have to use the product rule. So we basically, this whole term is just going to be negative, right, our negative sign right here, times the derivative of this one. So negative lambda times e to the power of negative lambda t times our original term right here. So that right there plus the other term in our product rule, which I'll draw out right here. It's going to be this derivative of this term right here, which we calculated as this, times our original one from up here. Okay, so now I've plugged those in. You can see all I did here was basically cancel the x with the x from down here, and now this is going to be x minus 1 factorial on the bottom. Now when I distribute this original negative sign that I have, right, it's going to cancel with our first term like so, and then it's going to basically have a subtraction right here. Okay, now I can just pull out this common factor right here, e to the power of negative lambda t. Also, one more thing, in this original term right here, for my first term in the iterator, right, x equals 0, you'll notice that when I plug in x, I'm just going to get my first term is going to be 1, right, plus all the others. But when you take the derivative of this, this first term is basically going to be 0 regardless, so we can basically just start the iterator of our derivative at 1 instead of 0 here, which is what we should have done. If x did start at 0 down here, well, then we'd get 0 minus 1 factorial, which doesn't make any sense. This whole term right here would just be 0 anyways, right? So we can just start x at 1. 1 in this term. Now the thing to realize is that these two sums right here are almost exactly the same. They're going to have a lot of similar terms. For instance, for my first term, x equals 1 right here, I'm going to get 1 over here, and I'm also going to get 1 over here. And then my next term will also be the same, right? For example, when you start enumerating this sum, right, you're going to get this. It's going to keep on going. And you see that when you start enumerating this whole term right here, you get lambda times this sum in here. And you can see that when we distribute the lambda, these are basically going to be identical, and we're subtracting. So a lot of these terms are going to cancel. So to get these two summations to look more similar, let's just do a little change of iterator on this one over here. Let's let m, our new iterator, be equal to x minus 1. Then when we do that, we can get these two sums to look more similar when I replace the x minus 1s with m's. And then for our iterator, x is starting at 1. When we plug in x equals 1 over here, we get m equals 0. And when we plug in k minus 1 for x over here, we get m equals k minus 2. Also, to swap out this x right here, all we can do is see that x is just going to be equal to basically m plus 1, right? If m equals x minus 1, then x equals m plus 1. So we can replace this right here with m plus 1. And now look at how similar these terms look, right? We can distribute this lambda inside of here, first of all, right? And then we're just going to get a lambda to the power of x plus 1, and now they look exactly the same. The only difference is that our iterator is going to different values. But when we take this sum right here, we're basically just subtracting off the first 0 to k minus 2 terms. So the only term that's going to survive in this subtraction is our k minus 1 when we plug that in for x in this sum, right? Okay, so now let me make some more space down here. So the only term that's going to survive, we still have this e to the power of negative lambda t that we're multiplying everything by, and the only term that's going to survive is when we plug in k minus 1 into this equation right here. So what happens when we do that? Well, when we plug in k minus 1 for x in that term, we get lambda to the power of k minus 1 plus 1, so just lambda to the power of k. When we plug it in right here, we get t to the power of k minus 1, and then on the bottom we get k minus 1 factorial. So that is our final answer. We have a lot of nice cancellations. So boom, that right there is the PDF of the gamma distribution. We have lambda to the power of k times t to the power of k minus 1 times e to the power of negative lambda t divided by k minus 1 factorial. So yeah, very complicated looking PDF. In this PDF, we have this lambda, which represents our rate parameter, so the number of events that we expect to happen within a certain time period. T, on the other hand, is the specific time period that we are looking at. So lambda t, this term right here, is just going to be the number of events that we expect to happen within that time period t. And k right here represents basically the kth arrival of the Poisson process. There's a ton of different ways that people write the PDF of the gamma distribution. This one right here is basically called the rate form, and there's another one called the scale form, where all you do is you take theta and you set that equal to 1 over lambda. So lambda is just equal to 1 over theta, and then you could just plug that in, and that's how you get that PDF. So this right here would be scale form if you plug this in, and then this one right here would be rate form. And people call k the shape parameter and lambda the rate parameter. And you can also generalize this further by not even forcing your k to be an integer, right? When we were doing it, k was basically the kth arrival in a Poisson process, so it's going to be an integer. But if you wanted k to be a non-integer, then you could generalize this factorial on the bottom, right? Factorials only take integer inputs, but you could basically have something called a gamma function, which looks something like this. So you could have gamma of k instead of k minus 1 factorial, and this kind of generalizes the factorial to non-integers. So there's a ton of different ways that you can write it, but this one right here is going to make the most sense in the context of the Poisson process. Also, one more thing, k represents the kth arrival of the Poisson process. You remember in QP 111, we were doing the exponential distribution, which represented the first arrival of the Poisson process. So if we plug in k equals 1 right here, then you're just going to get lambda to the power of 1 times t to the power of 0, so 1, and then e to the power of negative lambda t, and then that's going to be all on 1 minus 1 factorial, so 0 factorial. 0 factorial is obviously equal to 1, so this is what you'd get when you plug in k equals 1 into the gamma distribution, and that is also the PDF of the exponential, which we showed in QP 111, so it all makes sense. So yeah, one more time, the gamma represents the kth arrival of the Poisson process, and the exponential is a subset of that represents the first arrival of the Poisson process. And this one right here is the PDF of the gamma distribution in the rate form, which is what we wanted to solve in part C. So this question is wrapped.